Thank you very much for having me here. And this is very honored for me and our company and Pascal. So today the title is the solving differential equation in multiphysics applications using quantum machine learning. So let's go to the next page. So actually, inside of a company, there are a lot of problems to be solved for the some kind of efficiency, economically or something like that. So especially, we have some problem of multiphysics problem, so which is consuming computing power a lot and required a lot of human interaction as well. So I guess that I'm thinking that any physical phenomena can be represented by the set of partial differential equation. So inside of a company, there are a lot of things can be resolved by solving the differential equation as well. So if we have a very good differential equation solver, that is very useful for resolving a lot of problems and some give contribution to the company's business as well. So there are several ways of resolving the differential equation conventionally. So mostly actually we are using some kind of commercial tools for resolving that kind of computational things. So especially those things are mostly based on the grid or mesh-based things. That is a kind of the numerical approach. So in that case, that we can increase the some kind of one-dimensional, two-dimensional, three-dimensional, and we can increase the space size and the time size. I mean, the computational burden is increasing, exponentially or something like that. So there should be some resolve of this kind of problem. So recently, we found that physics-informed neural net, that is the one of the promising candidate for resolving that kind of problem. So, but our team is kind of a quantum-based team, so we need to apply this kind of thing to the quantum side as well. So that is the some kind of introduction for why we are working on the multiphysics problem by using the quantum computing-based solver. So if we, as I told you, if we have a very good differential equation solver that can apply the battery problem, the fuel cell design, and biomedical, and especially directly resolving some kind of thermodynamics and aerodynamics and fluid dynamics or something like that. So let's go to the next one. So anyway, we are going to have to resolve the differential equation. But we searched a lot of companies in the world. So one of them is like the Pascal. Pascal has a very good differential quantum circuit, which has some good characteristic of efficiently solve some kind of data input and output problem. And they doesn't require the QRAM. So most of our algorithm is based on the QRAM, but QRAM is not available right now. So we have to apply this algorithm to our real problem. So we have to find the algorithm which doesn't require the QRAM. So DQC is not requiring QRAM, so that is a very good candidate for our application. So basically, natively, the DQC can solve the nonlinear problem as well. So And then, so they are also used some kind of direct differentiation method. So that's why we are entering the LG Pascal collaboration stage, and we build up some kind of 3 years collaboration between the two companies. So this is the first year result, and this kind of, I mean, I apologize that I cannot include everything because due to the some kind of confidential limitation or something like that. So, but you know, you can easily understand how we resolve this problem by applying the conventional method and the quantum-based method. So, our hope to achieve the industrial advantage derives directly from the expressivity by quantum circuit, and by porting the quantum domain, so the typical advantage of physics-informed machine learning can be adopted. So let's go to the briefly explaining the physics-informed neural network. This is also a very recent area. So, I mean, the approach is to apply the neural net to resolve the differential equation. So right side, you can see some kind of the graph. So there is a kind of the trial solution, and there is the kind of exact solution. So exact solution is the solution of differential equation. Trial solution consists of some kind of we can easily imagine that some kind of the set of the function, like we can easily think that that can be a Fourier series or something like that. So by you know, like by doing some including some set of the equation. Starting from that, we can, you know, pursuing the exact solution by using the trial solution by controlling the updated weights. So this is kind of the overall explanation about the physics-informed neural net. So as you can see, the some kind of the general, you know, network, and there is the trial solution, and I mean, the most important thing is that we have to build a very clever loss function. So loss function affects the performance a lot. So in case of the loss function, I mean, that is directly from the differential equation. So differential equation loss and the boundary condition. We can reflect the differential equation directly and the boundary condition directly as well. So pretty much about the physics-informed neural net, this kind of concept is almost directly to the quantum side. So most of the scheme is almost the same as it is, but the quantum side is a little bit different about the neural net. Instead of using the conventional neural net, we are using the variational quantum circuit instead. So variational quantum circuit can be known as like the kind of ansatz. So this is pretty much the same as the physics-informed neural net, but a little bit different thing is that there is the feature map. So feature map is a kind of preparation for the input. So there is consists of the several the function. So which is the kind of is the combination of sets of equation. So at this time, we are using the Chebyshev function instead of the Fourier function. So I mean, the performance is kind of dependent on which function we can choose. But at this time, the target function, the Chebyshev is the most the better performance than other ones. So that is why we choose the Chebyshev function here. So this is an explanation about the quantum algorithm for solving partial differential equation. So even if we use the physics neural network, so physics neural net is known as like the notoriously hard to converge when facing complex scenarios especially. So in order to boost the convergence, we took the couple of techniques like the domain decomposition. So in order to boost the convergence, we divide over time domain like the 3 or 2 or 4 or something like it depends on some kind of the complexity of equation. So another thing is that another important thing is that the boundary pinning thing. So even if the trial function is converged to the target function, but sometimes the boundary pinning is kind of the like the bad impact to the convergence. So most simple pinning boundary is that definitely we knew that the boundary condition is like the constant, right? So if we minimize the loss function, definitely that boundary condition should be effect, right? The boundary condition is kind of the same as the constant number. So that kind of aspect can be applied to the boundary pinning strategy as well. That is the most simple boundary condition, but the boundary condition can be adaptively adjusted and adaptively reflect to some kind of equation as well. So those things are also applied to the quantum side, and we can see some kind of convergence boost up a little bit. So we think that that kind of strategy is very useful for the conventional one as well as the quantum side. So this is kind of very basic idea for differential equation solver we have implemented. So there are a couple of, 3-page or 4-page for the some kind of result we can get from the algorithm. So this is the Newtonian mechanics result. So actually, this is kind of the two-dimensional differential equation. So we used the 3 different QNN, and each QNN has 2 qubits and 6 steps. So that's very simple, but we can solve the differential equation by using this kind of simple QNNs. So this is kind of very, like the little bit cute. So actually, the particle is moving based on the electric field. So electric field is given for this experiment. So the particle is moving according to the electric field, based on what you expect. So this is the simulation particle things, but in order to, this experiment is based on the given force field and the torque field. So in order to check the torque, how torque field is working. So we intentionally make a shape like that. So we can usually, use the some kind of the particle, but this case, in order to analyze the torque field, we have to change the shape a little bit, and that is not the fully symmetry. So especially, the one thing is that the center one is the upper side and the lower side. If upper side and lower side has a different the different physics attribute. So the one thing is it can be, like attractive to the upper side. The other thing is the repulsive to the upper side. So that is working exactly what you expect. So, if I summarize this page, we use the 3 different QNM for the two-dimensional Newtonian mechanics. Each QNN has the 2 qubits and 6 steps. That's very simple, but that's kind of powerful to resolve the differential equation. So next one is the previous page, like the electric force and the torque force was given. But in this page, we are trying to resolve the electric field and something like that by applying the previous described the algorithm. So let's see the result. This is compared with the finite element method. The finite element method is very classical, and that's very also orthodox things. So if we apply the very like the rectangle size the electrode, so around the electrode the electric field is resolved very well, and there is no any big difference between the result of our algorithm and the finite element method. So the next one is even if we apply the round type electrode and the triangle electrode and the different the different places of the electrode, all those things are very all of them has a very good result compared to the FEM solver. That is what we observed so far. So next one is the kind of the convergence comparison result. So it's very hard to compare the conventional one and the DQ-based one directly. Looks like this is not the apple-to-apple comparison, but we can observe exemplary. So we just want to share the observation, but the theoretical analysis cannot be done yet. So later we have to analyze why we have this kind of the better stability and the better trainability and the better convergence rate. So that is what we are going to do later. So this is these 3 pages we have done. We get the result. We get the information as a result from our algorithm. So the next page is about the kind of the summary. So actually, in this presentation, we have addressed the different machine learning inspired alternative method to address the partial differential equation that can be challenging for conventional method. As I already told you, the mesh-based and the grid-based requires a lot of computational burden. So we need to find a very efficient way of resolving the differential equation for the economic, the business impact for our internal the business. So the next one is the how quantum computing can play a role in this paradigm shift. So augmenting the tools available to the classical ML approach with the QML. So, I mean, in order to implement QML, the quantum machine learning algorithm, we starting from the machine learning side, the conventional machine learning side. So actually, in practically, we are implementing the conventional machine learning and the quantum side of machine learning at the same time to lower some kind of risk we may have. So currently, we have done for the two-dimensional aspect, but we are going to do for the three-dimensional or something like that. So far, I mean, as you know, the quantum computing has a that's not a good fidelity. So we are developing the algorithm based on the quantum simulator so far. So eventually, we are applying the quantum machine learning algorithm to the real quantum machine. But right now, we are developing the machine learning algorithm based on the quantum simulator to exclude the impact of the fidelity issue. So the good thing is that if we use the DQC has its own state preparation things, and the PIN doesn't require the big data. So that is a very good aspect for adopting the PIN and the DQC for our differential equation solver problem. So anyway, we have done for the 2D, and we are going to 3D. And right now, we are only resolving the Newtonian problem, but we are going to expand a lot of other problems like fluid dynamics and aerodynamics and some kind of heat transfer problem, as well as the turbulence problem as well. So that is what we have done so far in less than 1 year. So this is very, practical thing. So there is no any theoretic one. But anyway, we have to resolve our real problem. So we are focusing on some kind of the real, DQC, quantum circuit, quantum algorithm. So that is what we have done so far. So thank you very much.
All right, now session is open for the question.
Hi, thank you. Thank you very much for a very interesting talk. So if I understood this correctly, the number of qubits you use for these variational circuits only depends on the choice of your feature map. So do you expect anything different if you use more, if you use more qubits, if you use higher dimensional feature map? Do you expect something different? Do you expect improvements?
Yeah, actually, we have tried the several different qubits. So, the number of qubits is also kind of the resource to be optimized, right? So, actually, we use the different number of qubits, but there is no, we can, by optimizing some kind of circuit and some kind of strategy, so we can reduce to the 2 qubit. So actually, I don't expect that this is a proper answer to your question, but that is the status.
Oh, I see. So after doing some optimization, you said you observed that just using 2 qubits worked better? Is that what you mean?
Not better, but almost the same result by reducing the number of qubits. So which means that at the early stage we can attack the problem naively, right? So and then we can find some more optimization things, and then we can reduce the resource as much as we can. That is the natural way of dealing with the problems, I guess.